So our next speaker is Faseela from Ericsson. She comes from Ericsson Bangalore R&D, India. She is the software engineer there, and she has been working with Ericsson for 3 years on the development of SDN controller. She's going to discuss how to improve the OpenFlow setup times, right? Thank you.
Hello, everyone. Actually, this is my first conference ever. I'm really excited to be a part of such a big event. So my presentation is basically about the impact of control channel messages on the performance of OpenFlow networks and analysis of the same behavior in a multiple controller architecture. Okay, so talking about myself, I hail from a small state called Kerala in the southern part of India. I'm married. And I joined Ericsson as a fresh graduate in 2010, along with my 24 batchmates. And now it has been almost 3+ years. I worked for Ericsson Network Policy Management, Element Management, and now I am a part of SDN controller team. So this is the agenda. First, we'll see why we require a multiple controller architecture in SDN. And then we'll see the various factors affecting the OpenFlow network performance. And then we'll look into handling dynamic network conditions like link failures, control channel congestion, and so on. And then I propose 2 solutions for dynamically migrating a switch from one control domain to another. It's basically a controller-initiated migration or a switch-initiated migration. So why distributed SDN controller? The answer is very simple. A single centralized controller lacks scalability. Firstly, the amount of control traffic destined towards this single centralized controller may increase with the number of switches in the network. Secondly, if the diameter of the network is large, no matter wherever the controller is placed, certain switches will definitely incur large flow setup latencies. And since the performance of the system is bound by the controller processing power, when the traffic increases, definitely the performance is going to decrease. Also, distributed SDN controllers are required for load balancing and fault tolerance. So these are the various performance factors affecting the OpenFlow network performance. Flow arrival rate is the rate at which the packets enter the network. Flow matching is the time taken by an OpenFlow switch to match an incoming packet to a corresponding flow table entry. And the control channel overhead includes all the control channel messages happening between the switch and the controller. Controller responsiveness is the time taken by a controller to respond to a particular OpenFlow switch. And then flow installation cost is the cost of installing an end-to-end flow. And definitely, if you have multiple controllers, there is a synchronization overhead across the controllers. So the background for this study is some of the experiments I conducted on the OpenFlow control channel behavior. I used a tool called OFNet, which is a troubleshooting and debugging tool developed by one of my colleagues. The tool is to be open sourced soon. So this is a topology diagram captured using this OFNet. So I started with a topology of 40 hosts and 7 switches with a single controller and did a simple ping. So the ping was done from a host connected to switch GS2 to a host connected to switch GS6. The various control channel messages are also shown in the diagram. So these are the control plane transactions involved in just a simple ping. So as can be seen, for each ping, all the intermediate switches in the ping path sends a control channel message to resolve the forwarding decision. So these are the control plane message counts for the same. So this is the case for a simple ping. So consider the case of live traffic where a number of flows will be involved. So then I started with a traffic generator, where the generator was generating flows at a rate of some 30 to 50 flows per second. So these are the control channel message count again. And the forwarding state of the network will look something like this when you do some traffic generation use case. So again, this is captured using this OFNet tool. And I've just captured the various graphs, performance graphs for the same use case, including the flow arrival rate, flow setup latencies, number of packet-ins coming to the controller, and packet outs going from the controller, and so on. So from all these statistics, it's very clear that reactive flow setups incur a major portion of all the control channel messages, including the packet ins, packet outs, flow modes, statistics collection, all these things. So consider a multiple controller scenario where a subset of the total number of switches is controlled by one controller. So in such a case, how do you handle dynamic network conditions is a challenging question. For example, if one portion of your network is incurring a large number of flows and another portion of the network is remaining underutilized, how to detect such conditions and handle them is like a challenging question. So the major challenges as of now is the switch has a static configuration of what and all controllers it should connect to. And if you want to migrate a switch from one controller to another, there is definitely a synchronization overhead because we need to synchronize the states also. And as of now, the switch initiates a control connection. And for this fluctuating networks, if you don't have a strong load balancing algorithm, you will end up migrating the switches back and forth. So these are the various metrics used to make the load balancing and switch migration decisions. So they are the number of switches connected to the controller, the number of open flow messages a switch can generate, number of packet-ins a controller can handle, and the number of packet-outs or flow modes a controller can generate. So there are two ways to approach this problem. Either the controller can monitor the network and decide when to do the migration of a subset of its switches, or the switch can monitor its control channel and decide when it wants to migrate to a different controller. So first we'll see the controller initiated migration. So here we have one master controller and n slave controllers for a particular switch. So there will be a monitoring module which monitors all the controllers in the network and their controller to switch assignments. The monitoring module is also responsible for monitoring the control channel latency. This can be done using the echo request reply messages of open flow. Now once we'll set one threshold for each controller for the maximum number of flows a controller can handle. So once this threshold is crossed, this controller selection algorithm can be initiated. The algorithm can be briefed something like this. You will have a set of, just retrieve the set of switches connected to a particular controller and sort them in the descending order of the number of flows they are generating. Take the first one from the list and see the set of feasible controllers for this particular switch and select the controller with minimum latency for this particular switch. And once this controller selection is done, the switch migration can be done using the open flow role request message. So for a graceful switch migration, I'm using the same mechanism as mentioned in the paper towards an elastic distributed controller. It will be something like this. First, you will have one master controller and a slave controller, and you want to migrate the switch to the slave controller. The master controller first sends a start migration signal to the slave. The slave changes itself to equal mode. Once the equal mode controller is ready for migration, for this graceful migration, the master controller sends a dummy float to the switch, and then a barrier request and reply to synchronize things. And then when a dummy flow is deleted, both the controllers will get the flow removed, and this is taken as a trigger. From the equal mode controller as ready for migration. And once this barrier request reply is done, the migration process is ended, and the final equal mode controller changes itself to the final master. and the other one will change to slave. So this is used because we don't want to lose any messages in between of this during the switch migration thing happening. And then we'll see how the switch initiated migration will work. Here we are using the concept of anycast load balancing. So we will be having the high availability controller pairs sitting behind the anycast load balanced peers. The load balancer will be responsible for monitoring the backend cluster for the various load parameters, whatever we discussed previously. And there will be an anycast resolver sitting in between, which can monitor the control channel. So the switch contacts this anycast resolver to see whether there is a change in the unicast IP resolve for this anycast address. If there is a change, the switch initiates a new connection to the new controller without tearing down the previous connection. So after the resync or the synchronization is done, the switch can gracefully terminate the previous connection. So the same thing whatever I discussed now. So to brief on what we already discussed, we first looked into why we require a federated SDN controller architecture, and then saw the various factors affecting the open flow network performance, and then saw two solutions how you can migrate a switch from one controller to another dynamically. And then the future scope for the study is the open flow configuration and management protocol, which motivates remote configuration of data flow paths. And then I have to see how to avoid frequent switch migrations, and then also configurable switch migration, because as and when required only if I want to do the switch migration, I have to make this a configurable parameter. Okay, that's it from my side. Any questions?
Thank you so much, Faseela. Any questions? Okay, so I'll ask one. So you basically did the analysis for how you can optimize the migration of the switches, right? Yes. Now, have you done some analysis on the latency introduced for unknown traffic flows that hit the switches, and what is the time and the scale?
That's the graph whatever I showed first.
So the many graphs that you have.
Yes. So that has the flow setup latencies when you run.
So how did you do that? What are the parameters that can be improved or that can be minimized?
So most of the study was done for this reactive flow setup. That is when a table entry is not there for a packet and you have to contact the controller to resolve it. So in such cases, one improvement can be like you have timeouts for each flow table entry. So if a flow table entry is expired, you will have to again contact the controller to resolve the forwarding decision. So in such cases, how you can dynamically configure this flow timeouts so that the entry is always there whenever a packet comes for the same thing. Such optimizations we can really do using some network analytics applications and so on. So I'm doing some studies for the same.
So maybe next year we'll look at that.
Yeah.
Okay, thank you.
Thank you.
So we break for coffee, and we'll be back at 10:30 sharp. Thank you.